The recent identification of a third confirmed interstellar object to pass through our solar system marks a significant milestone in modern astronomy and highlights the growing capabilities of global scientific collaboration. On July 3rd, astronomers from around the world announced the discovery of this rare visitor, designated 3I/Atlas, an object that originated far beyond the boundaries of our own solar system. Among the contributors to this discovery was a doctoral student from the University of Michigan, underscoring the important role that early career researchers play in advancing frontline scientific knowledge. The detection of 3I/Atlas is not merely an isolated achievement. It represents a broader shift in humanity's ability to detect, analyze, and understand objects that form in distant regions of the Milky Way and briefly pass through our cosmic neighborhood. Interstellar objects are fundamentally different from asteroids and comets that originate within the solar system. While native solar system bodies formed from the same disk of gas and dust that gave rise to the sun and planets, interstellar objects were born around other stars, shaped by entirely different environments, temperatures, and chemical conditions. As a result, each such object carries with it a record of processes that occurred far beyond our reach, offering a unique physical sample of another planetary system. When these objects pass through our solar system, they do so at high speeds and along hyperbolic trajectories, meaning they are not gravitationally bound to the sun and will eventually continue their journey through interstellar space. Because of their fleeting presence, detecting and studying them requires both rapid coordination and highly sensitive observational technology. Following the discovery of 3I/Atlas, Astor Taylor of the University of Michigan's Department of Astronomy and Darrell Seligman of Michigan State University collaborated on a new scientific study aimed at exploring the physical and dynamical properties of this intriguing object. Their work represents one of the first steps toward understanding what 3I/Atlas is made of, how it behaves as it travels through the inner solar system, and how it compares to the two previously confirmed interstellar visitors. These earlier objects, often cited as groundbreaking discoveries themselves, fundamentally changed scientists' expectations about how frequently interstellar material might pass through our region of space. The detection of a third object reinforces the idea that such visitors may be more common than once believed, though still challenging to observe. The study of 3I/Atlas allows astronomers to investigate questions that extend far beyond a single object. By analyzing its brightness, motion, and potential activity, researchers can infer its size, shape, composition, and surface characteristics. Any signs of outgassing, for example, might indicate the presence of volatile materials, such as water ice or carbon-based compounds, which could provide clues about the chemical makeup of the planetary system in which the object formed. Even the absence of such activity can be informative, suggesting formation in a colder or more radiation-rich environment. Each data point collected from 3I/Atlas adds to a growing comparative framework that will eventually allow scientists to distinguish patterns among interstellar objects and identify key differences between them and solar system bodies. For researchers like Astor Taylor, the discovery of 3I/Atlas represents the very essence of why observational astronomy exists. As Taylor emphasized, the goal is not only to find rare and scientifically valuable objects, but also to share these discoveries with the public and inspire a sense of wonder about the universe. Public awareness and enthusiasm are essential components of scientific progress, particularly in fields like astronomy that rely heavily on public funding and large-scale infrastructure. When discoveries capture the imagination of people beyond the scientific community, they help build long-term support for ambitious projects that might otherwise seem abstract or distant from everyday concerns. This connection between public interest and scientific advancement is especially important in the context of next-generation observatories. One prominent example is the Vera C. Rubin Observatory, which began operations this summer with support from the U.S. National Science Foundation and the U.S. Department of Energy. Although the Rubin Observatory was not responsible for the discovery of 3I/Atlas, its advanced capabilities are expected to dramatically increase the rate at which interstellar objects are detected in the future. Designed to repeatedly scan large portions of the sky with unprecedented sensitivity, the observatory is well suited to identifying fast-moving, faint objects that might otherwise go unnoticed. According to Taylor, it is reasonable to expect that Rubin could detect 1 or 2 interstellar objects each year, a rate that would quickly transform what is currently a small sample size into a statistically meaningful population. The prospect of discovering 10 or more interstellar objects is particularly exciting for astronomers because it would allow for comparative studies that are currently impossible. With only a handful of examples, it is difficult to draw firm conclusions about the diversity or typical characteristics of interstellar bodies. A larger sample would enable researchers to identify trends in size, composition, structure, and behavior, shedding light on how common certain types of objects are in the galaxy. This, in turn, could inform models of planetary system formation and evolution, helping scientists understand how frequently material is ejected from young star systems and how it travels through interstellar space. Beyond their scientific value, interstellar objects also carry philosophical significance. They serve as tangible reminders that our solar system is not an isolated entity, but part of a dynamic and interconnected galaxy. Material is constantly being exchanged between star systems, whether through interstellar objects like 3I/Atlas or through more subtle processes such as radiation and dust flows. Studying these objects allows humanity to glimpse the broader cosmic context in which Earth and its neighboring planets exist, reinforcing the idea that the building blocks of planetary systems may be shared across vast distances. The discovery of 3I/Atlas also highlights the importance of international cooperation in astronomy. No single institution or country can continuously monitor the entire sky, and the rapid identification and confirmation of unusual objects often depend on networks of observatories and researchers working together. Data must be shared quickly, observations coordinated across different wavelengths, and theoretical models developed in parallel with empirical studies. This collaborative approach not only accelerates scientific progress, but also ensures that discoveries are verified and interpreted with a high degree of confidence. As detection technologies continue to improve, the line between rare and routine discoveries may gradually shift. What once seemed extraordinary, the passage of an object from another star system through our own, may eventually become a regular feature of astronomical research. Yet even as such discoveries become more common, each new interstellar object will retain its own unique scientific value. Every visitor arrives with a distinct history, shaped by the specific conditions of its origin and the long journey it has taken through the galaxy. In this sense, 3I/Atlas is not just the third confirmed interstellar object, but a new chapter in an expanding story about our place in the universe. Ultimately, the excitement surrounding 3I/Atlas reflects a broader moment of optimism in astronomy. With powerful new observatories coming online, a growing global research community, and sustained public interest, scientists are better equipped than ever to explore the unknown. As Taylor noted, this is an auspicious time for discovery, and the anticipation of finding many more interstellar objects in the coming years speaks to the rapid pace of progress in the field. Each new detection will deepen our understanding of the galaxy and remind us that even as we study distant stars and planets, the universe occasionally sends pieces of itself directly to our cosmic doorstep.